Good afternoon, DoD Innovators. Thank you for joining us for today's webinar. I'm Captain Ashley Hollingsworth, Chief of the Directors Action Group at the Department of the Air Force Chief Data and Artificial Intelligence Office. As always, I am thrilled to be a part of this month's Innovation Connect. This month's webinar will spotlight the Defense Advanced Research Projects Agency's DARPA new GoldeVac, Golden Hour Extended Evacuation Program, which is intended to enhance the DoD's ability to successfully care for and then evacuate large numbers of wounded service members by essentially extending the golden hour during large scale conflict, disaster scenarios, or other mass casualty incidents. In addition, our speaker will also cover some of the latest innovative DARPA data and AI projects. Before diving into today's topic, I'd like to review a few housekeeping items. Non presenting attendees should ensure cameras are off and microphones remain muted. If someone has a live microphone while our speaker is presenting, please allow the moderators to mute that microphone. Please limit your questions to today's topic and avoid media related inquiries or commercial like promoting. Please use the chat throughout the presentation to direct your questions for the speaker during the Q&A session. Today, we are honored to have Dr. Adam Willis from the DARPA's Biological Technologies Office as our speaker. Dr. Willis joined DARPA in July 2023 as a program manager in the Biological Technologies Office. His research interests include biomechanics of brain injury, neuroergonomics of operational tasks, and critical care medicine. As a United States Air Force Lieutenant Colonel, Dr. Willis has demonstrated unwavering dedication to his work. In his most recent role, he served as the Medical Director of Joint Integrated Clinical Medicine with the Office of the Chief Scientist, 59th Medical Wing. He also served as a staff neurologist and neurointensivist at the Department of Defense's only Level 1 Trauma Center, Brooke Army Medical Center. Dr. Willis's commitment extends to academia, where he is an associate professor of neurology at Uniformed Services University and an adjunct assistant professor in mechanical engineering at Michigan State University. In 2022, he participated in the DARPA Service Chiefs Fellows Program on behalf of the U.S. Air Force. He is a trained flight surgeon and holds the Special Experience Identifier as a Critical Care Advanced Transport Team Physician Member. CCAT. Dr. Willis holds a Bachelor of Science degree in physics from the University of Notre Dame, Master of Science and a Doctor of Philosophy in Theoretical and Applied Mechanics degree from the University of Illinois at Urbana-Champaign, and a Doctor of Medicine degree from the University of Illinois at Chicago. Dr. Willis's contributions to the field are nothing short of impressive. He is a recipient of the 2021 Air Education and Training Command Air Force Management School Outstanding Achievement in Operational Research Award and a 2022 Defense Health Agency's Continuous Process Improvement Award. His work has been published in over 20 peer reviewed journal articles and several book chapters. He has given numerous technical presentations and mentors military officers, medical residents, and engineering graduate students in research. Dr. Willis's expertise is also recognized in the academic community, where he has served as editor and reviewer for several scholarly journals and on government science and technology review panels. We are excited about today's presentation. Sir, the floor is yours.
Hey, thank you so much. I really appreciate the opportunity. Again, first of all, the CDAO team's been fantastic, and it's just really excited to be able to chat with you all both about what I'm doing within my program, but also give you a taste of what we're doing within DARPA, in this space. So I think we've got the screen available. So again, I can't thank you all enough for this opportunity. Let's see. So I sit within DARPA's Biological Technologies Office, and here in BTO, that's what we call ourselves for short. We look at developing capabilities that that embrace the unique properties of biology to revolutionize how we in the U.S. defend our homeland and prepare and protect our warfighters. We have two key buckets by which we like to sort of frame all of our programs. One is warfighting readiness, and the other one is operational biotechnology. Under warfighter readiness, we have two sort of sub-buckets, which we focus on operational readiness, as well as warfighter health and recovery. And under each one of those, we have subsets focused on medical countermeasures, diagnostics and assessments, but also tactical care and warfighter performance and recovery. On our operational biotechnology side, we have two, again, key buckets looking for sustainable operations, where we focus on biomanufacturing and supply chain, as well as a resilient infrastructure, as well as we have a sub-bucket of operational advantages, where we focus on novel sensor technologies and novel methods and materials. This is my team. Again, I am surrounded and absolutely blessed to work with a host of brilliant individuals across academia, Department of Defense, et cetera. And all of us have sort of sets of programs that we all either developed or inherited and continue to run to support DARPA's mission as well as BTO. We like to plot all of our programs as well as all of our sub-buckets into the framework of prepare, execute, and return. And listed here is how we've graphed out where we think our warfighter readiness portfolio sits, as well as our operational biotechnology. But again, wholly focused on developing technologies to support the warfighter within that cycle of prepare, execute, and return. So we do have a couple other programs beyond GoldeVac that I think all the participants here might be interested to hear. The first one is DTC, or DARPA Triage Challenge. And this program is looking at developing new ways to triage casualties, understand how sick they are, what we need to do to intervene, and do that at scale using basically autonomous vehicles, as well as leveraging artificial intelligence. FAB is using biotech, or basically artificial intelligence, to understand what is a reliable metric of, say, fatigue that we can detect from breath, as well as Somnus is looking at understanding the underlying biology. And this is, of course, harnessing biotech and AI to understand, what is the restorative effect of sleep on cognitive performance? A very fundamental question. Moving into more of the biotech space, we have NESD, which is focusing upon developing revolutionary neural implants, which could restore capabilities such as high fidelity vision, hearing, and speech. And N3, program actually I hold, is focused on how can we create reliable brain-computer interfaces for the able-bodied service member, be it through non-invasive or minutely invasive technologies. Additionally, we have a program called Bridging the Gap Plus, which is focusing on using biotechnology, artificial intelligence, to build literally bidirectional communication through the nervous system, specifically to basically bring back function to individuals with a spinal cord injury, whereby you literally can bridge the gap of that injury and provide that bidirectional communication. So that is just a subset of all the amazing work that the office is doing. I'm just a small part of this. Certainly, if you want to know more about any of the programs I spoke about, or anything else that's going on, please go to the website. It's very easy to use, and I think you'll find it fascinating. So moving on to my new program. This is called Golden Hour Extended Evacuation, or GoldeVac for short. I want to just highlight, and this is a key opportunity. We are soliciting proposals as we speak. The abstract window is closed, but that doesn't mean you can't submit a full proposal, and that is due June 4th. And certainly, if you have any questions about submitting, you could also go to goldevac@darpa.mil and ask any questions you'd have. And this BAA is live, and certainly if anybody wants to contribute, that would be great. So GoldeVac. GoldeVac is focused upon addressing the problem that our current golden hour operations, and when I say golden hour operations, I mean the policy as well as the effort by which if someone is injured to get that individual to a surgeon within 1 hour from point of injury, that model of care is not going to function well in either future conflicts or, dare I say, it doesn't function well in many current areas where we have operations. And I'll get to more about that. But the world we want to live in is, say, looking on the left side of the screen, is if, say, someone's injured, a medic could pull out a technology from a backpack, place a single intravascular line, hook that up to the machine, press go, and that machine starts delivering high-level intensive care medicine to that casualty. And that would include giving blood, giving medicines, giving basically keeping the patient warm, but also actually providing gas exchange. So if someone has a lung injury, you wouldn't need to do a crike or intubate them, but actually could support their lungs through gas exchange intravascularly. And this device should have a closed loop as well as perhaps a semi-open loop capability, whereby you could either augment the number of casualties that a single medic could take care of, say, while waiting for evacuation, but also that care could continue upon any vehicle of opportunity, be it a surface vehicle, be it an air vehicle, be it a ground vehicle, or be it even via an autonomous vehicle. And then this care could continue once you, say, reach that surgical facility. It could continue both before and after surgical intervention, increasing the hold capacity, say, of our typical Roll 2s. But this also could be utilized to increase the number of severely injured casualties upon existing tactical or strategic evacuation airframes. The overall vision is we want to provide this expert level care from near point of injury throughout the entire evacuation process. And why am I really focusing on the entire evacuation process? And this is not me. This is the National Academy of Sciences and Engineering pointed out that a defining lesson of trauma care is that surviving traumatic injury depends on reaching definitive care, which is the highest level of care possible, as soon as possible. And in previous conflicts, OIF, OEF, we were able to get done the whole sort of sequence of events that would allow someone to be successfully evacuated, really getting them to that surgeon within 1 hour, that was possible. But if you look at, say, the placement of area of operations and all of the infrastructure, the medical infrastructure that we had, say, in Afghanistan, you can see the distances were not particularly far. However, if we look to other potential regions of conflict, be it in Indo-PACOM, where clearly there's tyranny of distance, where you could be 1,000 kilometers from a point of injury and perhaps the nearest available Row 2. But this scenario actually already exists within Africa, where area of operations certainly could be 1,000 miles away from or 1,000 kilometers away from, say, the nearest Row 2. And what that means is there's no way that you're going to be able to get a casualty to a surgeon within 1 hour. Thus, we need a new approach. We need to buy more time to accomplish that evacuation. And the hypothesis is, and again, this is not just my hypothesis, but the hypothesis would be is that if you were to start early, high-level care immediately after TCCC and triage, you could buy more time to accomplish the evacuation, successful evacuation to that casualty to the next higher level of care, and then continue throughout the continuum of care. And there are models of doing high-level intensive care medicine outside of a hospital. Now, I'm using the critical care advanced transport team as an exemplar, but it is not the only model within the DoD by which this occurs. If you look at sort of just the general model of, say, a CCAT team, and looking on the left side, you see inside of the green box, here is that patient who's receiving care in the back of actually a C-17, I believe, in this picture. The patient is surrounded by a whole host of sensors, and those sensors are being seen by our control system, which is actually a team of a physician, a nurse, and a respiratory therapist. They take that information, make decisions, and then influence, or basically alter the actuators, which provide blood, medication, control the temperature of the patient, as well as even adjust, say, the ventilator and control how much oxygen they're getting and how much CO2 you're taking off the patient. But then all of those changes actually then go back into the casualty via some invasive interface. And our vision, if we accomplish our vision, is that we could bring that ICU level care, not just expand it, say, within the resource of, say, strategic evacuation airframes, but you could bring that high level ICU care through Medevac, CASEVAC, and even within to the prolonged field care to allow and buy us more time to accomplish the evacuations, which is challenging in future scenarios as well as some other scenarios. So with that vision in mind, what is the DARPA hard challenge? What are we going after? And we realized that there's absolutely been dramatic improvements in, say, automated critical care, closed loop control for fluids, closed loop control for gas exchange. That's actually developing well, greatly in part because a lot of the investments by the DoD. Another thing that is improving is the sensor capabilities, by which you could have small, compact sensor suites, which could provide you a very high-level picture or snapshot of patient state that could feed into those control algorithms. But the truly sort of the area that we wanted to focus in on is how do you get all that care into the casualty? How can you reliably put in a single small IV, relatively small IV, and have that deliver basically all the gas exchange, all the medicines, all the resuscitation, and make that cannula or IV small enough and easy enough that a medic, and maybe even someone less trained than a medic, could place in the field to initiate and then continue that care. And turns out that's a very hard problem, because first of all, to, say, accomplish the gas exchange, you typically need large amounts of blood flow through, say, some circuit that's going to oxygenate the blood. And providing high amounts of flow through a very small tube, that's actually a very hard fluid mechanics problem. You also need to worry about what are you doing to the blood if you push it through that small tube, or what are you doing to the blood that flows around, say, this tube that's in the vein? Are you causing problems such as, first of all, maybe injuring the vessel that this tube is in, but also are you causing damage to the red blood cells or some inflammatory reaction because the material you're putting into the human body is activating, say, an intrinsic coagulation cascade, et cetera. And then lastly, if we are to accomplish this, how do we do it efficiently so that we don't maybe require as much blood products or other equipment or supplies that would strain the logistics within whichever framework you are. So that's really the focus of what we're trying to bite off within the GoldeVac program. And there's, just a further challenge, sort of what these key challenges are is, first of all, like I said, getting enough blood flow through a relatively small cannula. And the reason you'd want a small cannula or relatively small IV into the patient is the larger the IV, the more damaging it could be to the individual, the harder it is to place. But currently, through current cannulas, you just can't get enough flow to accomplish, say, enough gas or basically help support the patient breathing enough. There's also the challenge of all the machinery that's pushing blood through, or the interactions of the blood around, say, the cannula. That needs to be optimized to prevent all of those challenges that could occur. We are also looking to accomplish non-pulmonary, namely, we're going to try and basically support breathing of the patient, not through their lungs, but actually through that intravascular access. And this is probably also going to require new ways of looking at avoiding clots, that sort of that activation that happens when plastic's in the body, so that you don't get clots that go into the vasculature and cause problems for our patient. So we believe that a smaller, safer, deployable cannula and gas exchanges are possible, and that's what we're trying to really prove. And we have sort of metrics built around to really test that hypothesis that it's possible to provide all the care that a severe casualty would need through that single, relatively small cannula. And we first need to show in phase 1 that it's possible to, first of all, support a bleeding patient. Blood loss and bleeding is the #1 cause of preventable deaths within service members that is unlikely to change in future conflicts. And so we need to show that we have that capability. We also need to show that we can provide the level of oxygenation and gas exchange for prolonged periods of time through that same cannula. And we've put some metrics of exactly how much oxygen should be delivered. And then it has to be through a relatively small cannula, say less than 15 French, or that's basically less than 5 millimeters. They'll have to show that capability via a large animal model and demonstrate that they're able to keep an animal at sufficiency, which is just basically a technical term for healthy or relatively healthy, as opposed to sort of circling the drain. In the second phase, which will be 12 months, we would then focus on bringing it all together to show that we can keep a polytrauma, namely an animal that's bleeding, as well as an animal that has a lung injury, keep that animal alive with sufficiency for up to 48 hours. We're going to be testing this both in a basically large animal model using an IV&V team. First showing that we can support in phase 1 the greater than 6 hours of hemorrhage, but in phase 2 get us that 48 hours of polytrauma. That means that every technology that's developed by Performer is going to be tested by a government partner. But we'll also, and I think this is going to be very, very important to really push this technology forward, such that if we succeed, we can rapidly get this into a fieldable capability, is having a systems engineering oversight, again, using a government partner with expertise in biotechnology to first develop sort of a technical interchange process between the teams and government stakeholders, but also start to develop and then critique and provide feedback to the design of what this whole system would look like to allow and ensure that we were set up that if we're successful, we could rapidly go to prototyping a whole system that would fit that form factor and accomplish the vision of the world we want to live in. So again, more specifically, what are we looking for in this program, and how does this fall into biotech and AI? Is we're looking for teams to develop, again, say new cannulas, that's the physical interface between, say, all the machinery and the patients, and perhaps the gas exchange circuit. That is what we're looking for, aggressive development. But we want teams to bring the latest in small, compact sensor technology to basically to this system, to build a breadboard system to cobbling it together, plug those sensors into developed or developing control systems that could be based upon artificial intelligence or more heuristic-based algorithms, and then also have that control system then control multiple actuators who then provide all that feed, basically all those changes, physiologic changes, back into the patient. So at the end of this program, or actually throughout all phases, we're looking to build a prototype, a breadboard prototype of a closed loop support system. And I'll just say one more asterisk of what do I mean by breadboard. The crude definition I'm using is that it's the minimum amount of integration required to show that it is possible to deliver the high level of care through that single cannula. And then each team will be demonstrating at our end of phase demonstrations as amongst themselves, but also for our RV&V at our IV&V partners, that they can accomplish those metrics that we put out in our phases. This is the overall program structure. Namely, we have first phase 1 is going to be 18 months. Phase 2 is going to be 12 months. And in the first, first phase, we're focusing on developing the technology, showing that they can support both a bleeding animal model as well as provide the oxygenation level support, have the breadboard level demonstration. And then we will have basically demonstrations at our IV&V partners that we can accomplish our metrics for bleeding animal and oxygen demonstrations. Another component of the program that we're not soliciting for in the BAA, but is important, is ensuring that there exists technology which could allow a medic or a relatively, or someone even less trained than a medic, to place this large IV reliably into a patient in the field. So we're looking at, and we'll be evaluating some of the robotic technologies that would allow placement with this vessel with relatively little skill. We'll also have direct engagements with the FDA to allow us to keep driving in a direction to reduce the amount of time that it would take to eventually create a fieldable product. And then by phase 2, we're bringing it all together to build that polytrauma cannula, as well as show that this would work on a polytrauma animal model that's reflective of the injury patterns we would see in in future conflicts. And our teams will also be generating the preliminary design review of what that collapsed breadboard system into the actual product, what that would look like, and so that we can start to evaluate what that looks like and tee up this technology such that we could be ready to bend metal and fabricate these devices with follow-on funding at the end of the program if we're successful. A key component of this will also be ensuring that we have a transition strategy, and we're going to accomplish that not only by interacting with the FDA to make sure we can get these capabilities through human subjects approval, but also with strong relationships with the DoD medical training community, as well as DoD stakeholders. One of the lessons that we've learned is that if you do not have training on how to use the technology, even if a technology exists, you can't deploy it when you need to. So we will be continuing to interface and interact with members within the medical training community, as well as getting their feedback to inform future designs to make sure whatever comes out of this program has a chance of being useful within the operational environment. And we believe that if we have aggressive FDA engagement, work with our training platforms, work with the DoD FDA experts, and make sure we have end user engagement, we can rapidly achieve the overall GoldeVac vision of that capability that could exist in a backpack and provide high level of care near point of injury throughout the entire evacuation process. And I just want to take a step back and say, exactly why are we doing this? I think it's clear to this audience, but it's sometimes worth saying is that, first of all, it's not me, but the National Academy of Sciences and Engineering also support this, that evacuation saves lives. You need to get someone to the highest level of care as soon as possible. We need the capabilities that allow us to accomplish that, and it's going to have to be for durations greater than 1 hour. But also think about what is the effect of knowing we have this capability to our service members. It's a morale boost knowing that you're going to have a high survival. If you get injured, you're going to have a high survival. And morale is worth more than training and experience and even size. Okay, this is very, very important to maintain the morale and keep the operational effectiveness of our teams. But also think about national will. If you look at any of the war games, these are publicly available war games, for large-scale combat operations. A key theme that emerges is that the U.S. must recognize the need to continue operations in the face of heavy casualties. And I would argue that we are much more likely to maintain national will if we can minimize the number of fatalities that would be occurring during large-scale combat operations in order so that we can, as a DoD, achieve our strategic aims. So bottom line, GoldeVac aims to provide disrupting technology to increase warfighter survivability in all theaters. So if you have any questions about maybe applying to GoldeVac, we're looking for excellent teams to do this. Please go to goldevac@darpa.mil. You can also look up the BAA online. And any questions you have will be addressed within the FAQ opportunity website. So that is my presentation. I'm happy to take questions.
Awesome presentation, and it's fascinating. I think this would be awesome to bring to the medical community, especially with the focus on possible future conflicts and a big focus on TCCC and getting everyone else trained, just kind of making sure that the field care that they can do, is efficient enough. But I think this is great as far as bringing a high level of care to the patient instead of focusing on trying to get the patient to the higher level of care. So, I mean, I think this is awesome. While I'm talking, everyone, please feel free to post your questions in the chat if you haven't already. But I do have one question. Would this device stay with the patient, or would the medics have multiple devices if it stays with the patient?
So I think first of all, thank you so much. And secondly, I think the actual conouts of how this would work are to be determined by once we know sort of we get through those preliminary design reviews that'll show us what the device actually looks like. My hunch, though, is that I would suspect you'd have a couple of these units, you know, or basically that the unit would probably stay with the sickest patient. So any patient that's relying upon this device for, say, gas exchange, you're not going to want to unhook that patient. You're going to want to keep that going because basically that's breathing for them.
Right.
However, other patients where that's not a problem, you could swap it out and then allow them to basically, if they're going into a monitored setting, you could unhook them and take them onto a monitored setting. Or maybe these things would get small enough that, you know, for all of your severe casualties, which if you look at some of the war games about, you know, how many casualties, say you have a casualty event, a large casualty event, what percentage of casualties would probably need this level of care? Ballpark, you look about 10%. So you might, if you could make this form factor small enough, perhaps you could have enough of these around that you could manage, or at least bring in via some logistical capabilities, enough of these units to support all the casualties that you have at once, and then it allows you to just maybe ship out only your sickest casualties while you're providing a high level of care for the other ones that don't need to go, say, right away in a setting where you have limited evacuation capabilities. Over.
Thank you for that. And one other follow-on question. In a perfect world, I know the process would be long, and I thank you for explaining the process as far as the testing and things go. But in a perfect world, say after all the proposals are in and the testing, when do you think we could possibly see this in the field?
That's a hard. And how about this? I think, you know, I can tell you what we hope to have done is, again, at the end of the program, we hope to have metal. We hope that we have plans ready so that we can start bending metal and building this device. As well as at the end of this, we hope to have a submission for that cannula, really the only part that goes into the casualty, have that ready for human subject testing. And human subject testing could take a bit of time, as well as the testing of these devices could take a bit of time, you know, perhaps on the order of a couple of years. But you could have a prototype that's ready to go basically a couple of years after the end of the program. And then the question comes down to is when we get regulatory approval to do the whole thing. And that's a much more difficult to forecast, but you know, a capability could exist, or at least a good working prototype that could be perhaps more mass produced. That could exist a couple years after the end of the program. That's my suspicion. When we could actually use it, that's a regulatory question. That actually gets a little more complicated. Over.
Copy that, absolutely. And I'm going to pause here just in case anyone else wants to come up on mic or post a question to the chat if they have one. Well, I absolutely, again, thank you so much for your time here that you've given us. Again, this is very fascinating, and as a member who has a little bit of background in the medical community, I did when enlisted. I was an air medical evacuation technician, so I'm super excited about this. This would be great. Had the opportunity to fly with CCAT teams where um, you all would give that super high level of care, of course, for those critical patients needing evacuation. And evacuation does save lives, absolutely. I know there's a lot that happens in between the time at the point of injury to actually getting them to, a fob or an e-meds and then to an actual airplane to get them to one of the hospitals. And I just want to thank you for your service and all the work that you've done up to this point. I just think it's just absolutely awesome.
Well, thank you
And
so
we,
much. And then again, go ahead.
I'm sorry, go ahead.
I was going to, yeah, thank you so much. I really, really appreciate the opportunity. And of course, if anybody has any questions about this program, certainly you can email FAQ at goldevac at darpa.mil, or you can reach out to me. Although I didn't list my email address. It's rather straightforward to figure out. It's adam.willis@darpa.mil. Please feel free to reach out to me. I'm happy to have conversations. And again, this is such a great forum you all put together, and it's a privilege to speak. So thank you.
Great, thank you. And Mr. Stephen Beck says, very good project. So
Thank you,
great.
sir.
But I want to thank everyone for joining May Innovation Connect. We are grateful for your continued support of DoD Innovators and the DAF CDAO. We have several pioneering projects underway and are eager to spotlight each speaker. We look forward to seeing you at our June webinar, which will feature the Navy Center for Applied Research and AI at the Naval Research Laboratory. Approved videos of our past events are available on the Department of the Air Force CDAO YouTube page. And as always, we welcome your recommendations for future Innovation Connect topics to our DAF CDAO communications mailbox. Thank you for your participation, and we look forward to seeing you again.